等一下看教室这边大家有没有问题，我们再讨论完作业题再提问吧。
OK。Okay, good afternoon, good morning, everybody. Professor Hang asked me to quickly go through the procedure for some of the assignment problems. Okay, the first one is problem 1 of assignment 1, and this, I gave you the notes afterwards. This is under dynamic stability. Okay, that's a new set of notes we did up. Okay, so if you look at this set of notes, we have example 2.1, and it is very similar to the assignment problem. Okay, very similar to problem 1 of assignment 1. Okay, so the only difference is in our assignment.
谢老师，我看不到你的屏幕。
哦，看不到啊，Okay, the first, sorry about that. The first problem is problem number 1 in assignment 1. And this is the structure. We have a vertical load P going downward. And I send you a set of notes on dynamic stability. Okay, if you look at this set of notes on dynamic and we have example 2.1. The load P is not vertical, but it's always along CB. So we have this force called a follower force. It always follows the direction of CB. And derivation of equations of motion would be very similar. So I will not go through this in detail. Okay, so you can read example 2.1 on setting up the equations of motion. The second problem is problem number 4 in assignment 1. Okay, so we have this structure. We know all the parameters, and we have a rigid girder of mass m, and it's supported by 3 columns. Okay, and汤老师啊，
哎，是，你好。
你在跟他们说的时候，他这个 roller 你们怎么处理呢？
这个 load 怎么处理啊？
这个 roller 就下面这个 roller support。
这个 roller support 就是有，这个我们当时训练，我们觉得是没有约束的。
对，这个就是没有约束，
没有侧向约束，对。
那你就只考虑了这个中间这个 column 是不是？
对，水平项是这样。
那他们的学生的问题错在什么地方呢？
学生有的就是在这个地方，的确他们有的是考虑了这2个侧柱，然后呢，还有就是最后的那个动力时程分析，在这个三角形的这个输入下面的动力时程分析可能没做好。
OK， 行，那我解释一下这个，So in this case, this is a roller. Okay, so when the ground moves, and this part will not move. Okay, so we separated the ground and the part of the structure. Now, if we have a column with a pin support, then in this case, this column would provide lateral constraint. And when we have a roller, it does not provide lateral constraint, okay, because the red part is moving, but the blue part will stay stationary. Okay, so just be careful. These two are different. For this case, this is moving, so we will have different situation. Okay, so let's do this. On page 2.1 of part 1 of the notes, we have these formulas. Okay, so if this angle is theta, we need a bending moment, we need a moment to give this a rotation, 4k theta, and This is 2k theta. When we have translation and this is delta. This angle is phi. So here we need a bending moment, or a moment 6k phi. Okay, and the shear force is 12k over L phi. 12k over L phi. Okay, so k is equal to EI over L, and phi is delta over L. Okay, so now look at this. So we will have displacement. In this case, that's x. Okay, so this column, the middle column, moves, and for the roller, it does not provide any lateral constraint. Okay, so we only have this portion. Okay, so let's call this length L. This is x. Okay, so we have this angle is phi. Phi is equal to x over L. And okay, so use this set of formula. We have a moment of 6k phi, and shear force on the column. On the column is 12k over L phi. If you look at the girder, then we have the shear force k over L phi. Okay, and the two outside columns do not provide any constraint. Now let's say if we change one of them, to a pin support. If it's a pin support, then you would have this case. Okay, so okay, now phi is x minus y0 because this also moves y0. Okay, so now here we would use if it's okay, so that's our angle phi. You would need these six. Okay, so this part is similar to this part. Okay, so we need 6 K phi. And there's no moment here because that's a pin, so no moment. And we have shear force V and shear force V. So you have V times L is equal to 6 K phi. Therefore, V is 6 K over L phi. Okay, so now if it's this case, then you would have shear force going this way, 6 K1 over L, and phi1. Okay, so now phi1 would be x minus y0, and this height is L. Okay, so that's for the case when we have a pin. And for the assignment problem, we have the roller, so we only have a K here. Okay, so apply Newton's second law. Okay, so we have M x double dot is equal to the force applied. And we have only one force, so that's minus 12 K over L phi. Okay, and it is equal to minus 12. K is EI, and it's 2EI over little L. L is L plus 1/3 L, so that much. Maybe just for simplicity, I still keep a small L. And phi is x minus y0 over L. Okay, so we have M x double dot plus 24 EI over L squared, x minus y0 equal to 0. And call this Z is the relative displacement. Okay, then x is z plus y0. So m z double dot plus, I call this a big K, K z equal to minus m y0 double dot. Okay, so this term is the equivalent earthquake load. Okay, so to solve our equation of motion, we look at the loading. This is the velocity, y0 dot t, meter per second. Okay, we need y0 double dot. So take derivative. We have a constant. Okay, so this would be 0.5, and this is minus 0.5. Okay, so our equation is z double dot plus omega 0 squared z equal to minus y0 double dot. Okay, so you have to separate this. So 1, when t is between 0 and 1 second. So that double dot is omega 0 squared z equal to minus 0.5. Okay, so that's quite easy to solve. The complementary solution is A cosine omega 0 t plus B sine omega t, and Zp is minus 0.5 over omega 0 squared. Okay? Because right-hand side
Professor,
is...
the right-hand side should be positive 0.05, right? 0.5.
Yeah, negative 0.5, because this negative sign. Right?
Okay. Yes, you are right.
Okay, so now Z is okay, so now use the initial condition. Initial conditions, it's Z 0 equal to x0 minus y0. Okay, so assume the base y0 is 0, so that gives us 0. And then z dot 0 is x dot 0 minus y dot 0. Okay, so that's also 0. Then we can solve this. Okay, so now once you solve this, and then you can evaluate z at 1 and z dot at 1. And this would be the initial condition. So phase 2. Okay, so now for phase 2, t is between 1 and 2. Okay, so for phase 2, then we have z double dot plus omega 0 squared, that is equal to 0.5. Okay, so now z t is a cosine omega 0 t plus b sine omega 0 t plus 0.5 omega 0 squared. And then the initial conditions are these. Okay, so then you can find A and B. Okay, then for phase 3, t larger than 2, the loading is 0. Okay, so we have 0 here. Now from here you find A and B and also evaluate Z at 2 and Z dot at 2. So the equation of motion is this, 0 loading. Okay, so then T equal to A cosine omega 0 T plus B sine omega 0 T. Okay, so now these are the initial conditions for this case. Okay, so that's the procedure. Any questions on this? Okay. Next is problem 1-3 in assignment 2. Problem 1-3. Okay, so we have this, and we want to, by assembling the individual member nodal loads, determine the load vector. Okay. Okay, so we have all the dimensions, and P1 is L P bar T, P2 is P bar T, and P3 is 3/2 P bar T. Okay, so we only look at the load vector. Okay, so I'll find the page number. Okay, so that's a problem 1-3 in assignment number 2. Okay, so the load vector is on page Notes, page 3.26. Okay, so we have PRT is equal to PXT CR X dx.